Today we're tackling the age-old dilemma of when should you put the cream in your coffee. So here I have a cup of coffee and it starts off at 90 degrees Celsius, let's say. I take my little container of cream and I dump the cream in right away at time t equals 0. And my cream is going to be at 10 degrees C. So we'll call this scenario A. And we're going to wait, let's say, it could be, any time, but let's take 10 minutes of waiting time. And then we're going to drink the coffee and see, well, how hot is it? So in scenario B, we start off the same way, 90 degrees C for the coffee and a nice cool 10 degrees C for the cream, but we don't mix it right away. Instead, we wait for, let's say, 6 minutes. And that's 360 seconds. And then we mix it at time t equals 360 seconds. So that's scenario B. The temperature of the coffee, well, T1, let's call it. I don't know what that is yet. Temperature of the cream here, I don't know what that is either. That has to be computed. This version of the dilemma, coffee cream dilemma, is a little bit more complicated or challenging because I'm allowing the cream here to vary in temperature also. It warms up while the coffee is cooling down. So that adds an extra dimension. And if you think you have good intuition, you can close your eyes and think, well, what's going to happen here? And you might be a bit surprised at some of the results we get. It's kind of interesting. And let's get to it. This is going to be a mathematical thought experiment, and I think it's going to be very entertaining. And now we want to make a model of our temperature process using ordinary differential equations, or ODEs. We will derive an ODE that describes what's going on. So suppose we have this super hot object at temperature T, and we put it in a room where the temperature is TR at some distance, say sufficiently far away. Well, Newton's law of cooling says the following. Q is HA times T minus TR delta T. So for a small, let's use color. For a small time delta T, the amount of heat coming out of this and going into the room is proportional to the temperature difference, T minus TR. So the bigger this difference, the more heat is moving into the room. So that's quite interesting. Now, we use the following convention, Q positive, so positive heat means the following. Heat goes into the system in question, and a negative heat, Q is negative, well, heat goes out of the system. And here, this is positive. If you look at this, T minus TR, well, when T is very big, this is positive, and so the heat must be moving into the room. So I'll put an R here, subscript R, meaning this is heat from the perspective of the room, not the perspective of the hot object. Okay, so that's actually a peculiarity of how Newton's law of cooling is written. So it's better to be very explicit about this. Next, we have some other factors. We have this A. This is the effective surface area. So that's the area that participates in the heat transfer. And then we have H. H is the Newton's law of cooling heat transfer coefficient. And this is a kind of magical number because it doesn't assume any particular mechanism for the heat transfer. It could be anything. It's like an empirical constant. It depends on geometry, maybe depends on a lot of things. But it's best to measure this by experiment. We will try to estimate it and see what happens if we try to estimate this using some first principles. But this number is a kind of, well, it's like a lumped heat transfer coefficient that can represent both, conduction and convection all in one number. So it's all lumped into one heat transfer factor. Now let's look at some dimensions and units of this just to make sure that we understand what's going on. Dimensions of QR is energy, and that's joules. Heat transfer factor is the power over area times temperature Kelvin, so it's watts per meter squared Kelvin. And the area, of course, is meters squared. It's area squared. It's length squared. That's the dimensions of that. And delta T, dimensions of that is time or seconds. So, okay, when you plug all this stuff in, it works out. Dimensions of the left-hand side, we can write it like this. Dimension of the left-hand side equals the dimensions of the right-hand side. And that gives us some confidence that this is a good formula. If the dimensions don't match, if they're inconsistent, then of course the formula is no good. Okay, but if the dimensions do match, well, the formula might be good. So it gives us some confidence. Now, let's look at this from the point of view of the coffee cup. So now my system is the hot coffee cup. The first law of thermodynamics says that this here, delta U, the change in internal energy, is the heat plus the work. So the heat that went into the system, if the heat is positive, then the internal energy will go up. You see that here. And if the work done on the system is positive, then internal energy is going to go up also. For our case, the work is zero. It's purely heat transfer, so we forget about this. The first law says that the internal energy change is the heat that's gone into the system. That makes a lot of sense, right? But what is the heat that has gone into the system? It's not quite QR. That's the heat that left the system. So delta U is actually minus QR. Now it makes sense because delta U is negative. The internal energy of our cup of coffee will go down in some small time, delta T. And so to get a negative on the right-hand side, you have to put a minus here. Because remember, the way Newton's law of cooling is defined, Q sub R is bigger than zero. So this is what the first law of thermodynamics tells us. Now, also we know that the change in internal energy is the heat capacity times the change in temperature. This is the kind of like a definition of heat capacity, the relationship between internal energy and temperature and heat capacity. So we can plug these things, all these facts together. Like what we can do is we can take this and we can combine this with Newton's law of cooling. So we have delta U is Q is C delta T, and this is minus QR, but minus QR is minus HA T minus TR delta T like this. That's great. So we don't need to think about delta U anymore, at least not for now. And we can rewrite this as delta T over delta little t equals minus HA over C T minus TR. There, that's very nice. So far, so good. And, well, let's take the limit. So as delta T is very small, both of these become infinitesimals. We take the limit for a very small process, small changes, d by dt, dt by dt, d big T by d little t minus HA over C T minus TR. Very beautiful. Now I'm going to do something here. I'm going to define this C over HA We'll call this tau. Now, why am I calling this tau? Well, it turns out that this has dimensions of time. So let's try this. Heat capacity is joules per Kelvin, and H, well, we had H from before, watts per meter squared Kelvin, and area is meters squared. So we end up getting joules per watts, and that's seconds, and that's time. Okay, so well, 1 over second is seconds. So this has dimension of time. This tau is called the characteristic time. And it's quite an interesting thing. We will have a look at what it actually means in the next part of this video. But we can now write our equation in this really beautiful form. D by dt, look at this, 1 over tau t minus tr. So this is a very elegant form of the equation, and you want some elegance because there's a lot of complications coming. Hang on, let's close this bracket. So the more elegance we have, the better. In the beginning, the more elegance. You don't want to be swamped in a sea of constants and numbers and subscripts and so on. So this is it. This is our ODE. This is the equation that models how temperature varies. It works both for the coffee and for the cream, no problem. And now let's get to work trying to find a solution for this. We must find a solution to our differential equation. The technique will be separation of variables. So let's separate the variables. dt, t minus tr. And I take the little t to the other side, 1 over tau dt. Great. Variables are separated. So now let's integrate both sides. I'm beginning at a temperature T0. That's my initial temperature. And I go up to some temperature T, dt over T minus TR. Now you have to keep in mind that this T here is a dummy variable of integration. It's not the same variable as the big T here that we're looking for. Now on the other side here, I could just as well say 0 up to some time t, but I want to be a little more general than that, so I'll put t0 because, well, you'll see why. And this is dt. And again, this is a dummy variable of integration here. Okay, I'm sure you are familiar with that. Integrating the left-hand side, I get log absolute value of t minus tr minus that. And integrating the right-hand side, well, similarly, t minus t0. Okay, so this I can combine together, and I get t minus tr over t0 minus tr equals, okay. And what can I do about this absolute value signs? Well, okay, if my object is hot, then T will be greater than TR, like this. And of course, also T0 is greater than TR. So this is for a hot object. And so this entire factor here, this is going to be positive because it's positive over positive. Now for a cold object, T is approaching TR from below, so this is less than, and T0 is less than T, the room temperature, and so this is negative over negative, but that's positive, and so that's really good news. So I could get rid of those absolute values, but first let me close my bracket. All right, looks good. Let's get rid of the log, raise both sides to the power, to e to the power thereof. T minus tr over t0 minus tr is equal to e minus t minus t0 over tau. Very good. And we can now solve for t. T is tr plus this. T0 minus TR times E minus T0 divided by tau. And this is my general solution here. Now let's interpret the meaning of tau. Coffee begins at T0 and decays down to room temperature TR. But at some point here, tau, at some time tau, the temperature achieves a special value. So here we've computed it starting at time t equals 0. So it's the 1 over e point where it has dropped by 1 over e of its entire range from T0 to TR. So that's very interesting. That's kind of like half-life, but 1 over E life. So tau is like 1 over E life. Okay. In fact, you can compute this. We'll call it T wiggle. You can compute it using segment division. This is going to have a proportion of E minus 1. And this here will have a proportion of 1. And of course, they add up to E here. Okay, so it's a very pretty thing. And it's useful to know tau. When tau is big, you have slow cooling. And when tau is small, you have fast cooling. So computing tau gives us an estimate on how this temperature system will behave. You can close your eyes and kind of imagine it just by knowing tau. In order to get some quantitative results, we have to decide on values for our constants and parameters. So let's say I'm going to take 200 grams will be my mass of my coffee. And my coffee specific heat, that's a little C1. I'll take that to be 4,100 joules per kilogram Kelvin. That's specific heat. Specific heat capacity. And for the cream, well, let's take some reasonable values, M2. So 1 will be the coffee and subscript 2 will be the cream. I'll take 40 grams of cream, and specific heat capacity will be, let's say, a little less. I saw some figure in a book somewhere. That's specific heat capacity. And we can relate heat capacity to specific heat capacity like this with these formulas here. So it's very easy. You just multiply specific heat by the mass and you get heat capacity like that. Okay, so that takes care of that part. But now we want to estimate the areas. Okay, the effective areas. Okay, so let's write that down. Effective areas A1 and A2 for the coffee cup and the cream cup. How am I going to do this? Well, I got to make some assumptions about my coffee cup. So let's take a cup that has a certain kind of proportions. This is going to be 4 and 5. So y and x like this. X is this way and y is this way. So y over x will be 5 over 4. That's interesting. That's typical coffee cup proportions, I think. And we have a radius of the cup like this, and a relationship that x is 2 times the radius, yeah? So putting these two together, y is equal to what? Y is 5r over 2. So this is going to help me calculate volume and surface area in terms of just the radius. So I want to make it simpler to calculate those things by choosing some kind of proportion for my cup. My volume is the area of the base times the height y, and that's equal to 5 pi r cubed over 2. Now here, S is the surface area, but I'm only interested in lateral surface area. So what is lateral surface area? Let's say we have a cylinder like this, and I just want this surface area. I don't care about the top or the bottom, and we will see why very soon. So lateral surface area is the circumference, 2 pi r, times the height, y, and that is 5 pi r squared. Great. So I got these formulas for V and R. Okay, you're wondering, why do I need these formulas? Well, I kind of do need them because I need to know assaying dimensions for a cup that's going to hold 200 grams of coffee, right? So for a coffee cup, let's take a radius of 3.2 centimeters. And what does that give us? For volume, we end up getting approximately 257.4 centimeters cubed. And this is good because I want to fit in this cup 200 grams of liquid coffee, right? I don't want it to overflow. And what about my surface area? My lateral surface area is approximately going to be what? About 161 centimeters squared. Okay, that's pretty good. And for our cream cup is just going to be the same thing, only smaller. Same proportions, 4 to 5, just a lot smaller. And it's got to fit 40 grams of cream. Let's see if we could get that to work. We'll take a radius of 2 centimeters for the cream cup. And let's see, the volume, 62.83 cubic centimeters. And the lateral surface area, 62.83 centimeters squared. Very interesting. So as an exercise for you, explain this. Explain why they are equal. It's interesting. You tell me why well, they're not equal because the dimensions are different. This is length cubed, this is length squared. But why are the numerical value equal? All right, so I have to fit in 40 grams of cream in there. And cream has a lower density, something like 960 kilogram per cubic meter. So 40 grams is going to be larger, maybe, I don't know, like 45 cubic centimeters of cream. But it should fit in here no problem because my volume is big enough to hold that. And same here, this is big enough to hold the coffee. Okay, so that's great. I have values for A1 and A2. So A1 is going to be about 161 square centimeters, and A2 is the effective surface area of the little cup. Well, this is going to be about 62.8 square centimeters like this. So I've got those two values figured out now, and I'm almost done. I just need one more, which is actually the most confusing one to do, and that's the heat transfer factor. So let's estimate this. Let's try. Okay, we'll try a model that's conduction only. All right, so we have a wall like this. Here's our coffee cup. Here's the wall of the coffee cup. Let's say it's from here to here, the width is 5 millimeters. So we'll call that X. And this is something that doesn't have a very good conductivity. My coffee is in here, and the heat is going to go through here, conducted to the outside here, and we say it's at 25 degrees C right here. I didn't tell you the room temperature. Well, the room temperature I'm going to take to be 25 degrees C. Kind of a warm, slightly warm room. Right, so we'll say that the convection will take away this heat very effectively, and it's going to be 25 C at the surface here. This is a kind of idealistic assumption, and you will see in a minute. So if this is the case, then H should be approximately the K over X, where K is the conductivity of this substance. So for glass or ceramic, I think I'm being kind of optimistic to say it's about 1 watt per meter Kelvin over 5 millimeters. Okay, so I have to be careful how I do this. It's going to be 0.005 meters, and this gives me an H of about 200 watts per meter squared Kelvin. And I think that this is way too much. You'll see in a minute. Let's do an estimate of the characteristic time. You see how useful characteristic time is now. All right, let's move up a bit here. Well, when I plug in all those numbers, I get approximately 286 seconds, and I think that's quite fast for a coffee to lose 1 over E of its temperature range, So I think that this is a bit overly optimistic, or it estimates it a bit too fast. And what I think may be happening physically here, and if there are some engineers out in the audience who want to tell me more, that would be very interesting. Let me know in the comments. So here is my coffee. Okay, and what's happening is that the heat flows to the wall by conduction, but this is not 25 degrees. It's not. If you feel the coffee cup, you'll see it's always kind of hot. So it's not 25. It's not that efficient. What's really happening, I think, is that cold air goes in here and then becomes hot and takes away some of the heat, but not all of it. So it's not that effective as a pure conduction model would be. So I'm going to take an H. I just looked at curves of cooling objects, and I just took a wild guess, and I also want to make my graphs look good. So I took a value of 80 watts per meter squared Kelvin. And now let's look at another issue. Here there's going to be coffee vapor. If I put a plate on top of my coffee, which I'm going to do with both the cream and the coffee, then this coffee vapor is approximately the same temperature T as the coffee here. This is T, and the coffee vapor is about the same. So heat likes to flow from hot to cold. It doesn't like to flow from hot to hot. So I will assume that the heat going out through the top here is ignorable. So I'm going to ignore this surface area. I'll say that this is not part of my effective area. And likewise here, I have the table. And because I have the table, I don't have this effect of cold air coming in and becoming hot and then taking away the heat by convection. And so I will also ignore this area here. So now you see why I have taken the lateral area only, like here and here, you see. Okay, so let's fix H to be 80 watts per meter squared Kelvin. That gives me the best results. And there's one last thing I want to mention, that many of our constants have kelvins as the temperature, but we are doing computation in degrees Celsius. So why is that allowed? Well, I have never computed here in anywhere in these calculations a value for U. So there's no actual absolute value of internal energy. And we only have been working with delta U in the beginning. Okay. So it's all delta U. So the heat capacity equation and all that, it's all delta U. So if you're working with changes in internal energy, it's okay to stick to degree C. If you're working with actual absolute value of internal energy, yeah, you have to use the Kelvin scale for that. But we won't need to use it, so we could just safely just put in degrees Celsius values whenever we see kelvins, and it should be okay. All right, so I think we have all the data. Yeah, we have all the data, and now we're ready to look at some solutions. Let's look at some results for just plain black coffee and plain cream. We're not going to mix them together. For coffee, it looks like that with some data. T0 is 90 degrees C, and tau 1, case of coffee, is C1 over HA1, and we know these things. Big C1 is M1C1. And now for cream, we have the following curve with the data T0 is 10C, nice and cool. T2 is big C2 over HA2, and C2 is M2 little c2, heat capacity, specific heat capacity. So we have all of that. Let's see, what does the result look like? We have these pretty curves. Let's have a look at this. This is our coffee. Okay, and this is the curve for cream. And here I've added in the characteristic time, tau. So in our case, tau is, for the coffee, is about 637 seconds, so about a little more than 10 minutes. And in that time, it decays from 90 degrees C. It goes down to about 49 degrees C. Okay, that seems reasonable. Okay, and we see here the cream is warming up, coffee is cooling down, and they're both approaching the room temperature, which is about 25 degrees C. And here's that T wiggle thing, that magic 1 over E related value that I talked about earlier. But of course, the real magic begins now in the next part, where we're actually going to mix the coffee and cream. Scenario A, that's when I put the cream into the coffee right at the beginning. Okay, so I need a way to reason about this. I need to find out what temperature that mixture becomes, and I'll call that temperature T star scenario A. So star will be for things that have been mixed. Okay. I'm going to reason about it in a really simple way. I'm not going to think about actually mixing them. I'll put them in contact together. So this is the coffee, and this is the cream. And since this is hot and this is cold, there's going to be a movement of heat this way. And so the internal energy of the coffee will go down, and the internal energy of the cream, well, that's going to go up. But we know some relationships. Well, first of all, we know mass and energy conservation. That has to be true. But we know those heat capacity equations too. And we know that by conservation of energy, the change in the energy of the coffee plus the change in the internal energy of the cream, well, that has to be zero. It's not going anywhere, okay? So that has to be zero. Expanding these expressions and putting in the thing that we used before, we get this, where T1 is the coffee temperature at mixing, and T2, that's the cream temperature at the time that we're doing the mixing. Now, what should we be doing? Well, we can easily solve for this mixing temperature. We just need to do a bit of algebra, and we can easily get it. There's a pretty expression for the mixing temperature. So now we know the initial temperature of this mixture. Okay, so what's the equation of the temperature curve going to be now? It's this, and notice that our initial temperature is the mixing temperature. But we also need to know this tau A. So tau A is the heat capacity over H, and the cup is the coffee cup, so it's A1. But what is C? Well, conservation of mass. Well, our new mass, the mixing mass, is M1 plus M2. So I can call this Ca star. This is going to be a mixed version. So Ca star is C1 plus C2. We have to add them together. And we have to then compute a new value. This is a mixed value of tau. And from this, now it's easy to plot. See, it's not that, it's like easy to deal with this equation, easy to solve the ODE, but all the details are not that easy to get right. Here are the results. Let's have a look at this. It's very interesting. I have drawn onto this the black coffee curve. So notice that TA star is about 77.2 degrees. So dumping in that cream dropped the temperature significantly. So it begins here at this new initial temperature. So we drop down. Now, what's very interesting here, what do you notice about this? Well, look at this. The green crosses over the red. So the green is now above. There comes a point where my mixed coffee cream together is actually warmer than my black coffee. Why does this happen? Why? You would think that that's impossible. It's got to stay below. It's got to stay. Well, no, it doesn't, because tau scenario A is not the same as tau 1. This has a decay time, a characteristic time of tau 1. This has a characteristic time of tau A, scenario A mixed. They're not the same, okay? Because first of all, the new coffee cup has a new mass, M1 plus M2. And not only that, it has a new specific heat or heat capacity. And so the behavior is not the same, not at all. So I think that that's a little bit surprising, and it's really cool, and it shows. I'll put a star here to show that this has been mixed. So it shows that there are some aspects of this problem that was a little bit unforeseen. You know, I was a bit surprised by this, but then I realized, oh yeah, tau is not the same for these two curves. Okay, and now for the final scenario, scenario B. Scenario B is the most complicated of them all, but we have put everything in place so that we can solve it logically. We start with a cup of black coffee. It decays, temperature decays the same way like we computed for the black coffee. It's the same thing. And at 360 seconds, that's when the action starts, 6 minutes in. We have our cream that's been left out for 360 seconds also. And at this point here, we mix them. So we have these starred quantities because they're going to be mixed. So T1 is going to be the temperature of the coffee at 360 seconds, while T2 is the temperature of the cream at 360 seconds. And we're going to mix these two at these two temperatures and get a new temperature. We need to find the mixing temperature. What's the result? And we'll call that TB star. That's our mixed temperature for scenario B. And we find that exactly the same way using thermodynamic, conservation of energy, and all that stuff, just like we did for scenario A. And I'll just give you the answer here. Is the same like before, except remember, these are taken at 360 seconds. And those are easy to find because we have curves for those. We have a formula. We just plug in T and we get the answer. Okay, however, we also have a mixed version of the characteristic time. That's a mixed version of my heat capacities. H remains the same, and this is a cup surface area, and CB, again, this is C1 plus C2. So I have to put that into my formula. So my formula for the curve of the mixture is now, it's now this. And look here carefully, I finally had a use for this. I told you that we will need it. I am starting a new curve at exactly T0 equals 360 seconds. So this is a piecewise curve. This is going to be from 360 seconds onwards. So from, let's summarize this. From 0 seconds to 360 seconds, it's the same as the black coffee curve. But from 360 to onward, well, it's a totally different curve. It's the mixture curve. It's going to have a different heat capacity, different mass, different tau, different starting temperature, and it can all be computed. We know everything now to compute the results, and I'll show you a beautiful graph of the results now. There it is. Let's have a look. So for this section here, this is the same as black coffee. This curve, the red curve, that's scenario B. So green, let's write that down here. Green is scenario A. That begins at 77 and continues. So that's A. Scenario B is this red curve. So this starts off, there's the same as black coffee, but then there's this sudden drop here at 360 seconds where I dump the cream in. Notice the change in temperature isn't so much because the cream actually is warmer here than it is here. So it makes a difference, but it's enough to drop the temperature below the green curve, below A. So this is B, below A. Now, the interesting thing is at this point here, okay, after 360 degrees, tau mixing of A, scenario A, is exactly the same as tau mixing scenario B, because I've mixed them. They're actually the same thing, because I'll write the formula down here. Both of them are going to have exactly this tau. So it's the same after this point. Here, the taus are different. Before the here and here, tau is different. Tau, this is tau 1. This is tau A star. They're not the same. But here they are the same. So because we start below green and they have the same characteristic time, there's no way this red curve could ever go back up. So if I now drink my coffee at 10 minutes, that's 600 seconds. So which is hotter? Well, green is hotter. Scenario A is hotter. So we did it. We figured it out. The famous coffee dilemma. We did it. Or did we? Did we figure it out? Well, let me propose something to you. How do you know that this drop is going to bring you below the green line? So that's my question to you. Can you prove? Can you prove that B goes below scenario A? Can you prove this for all parameters? You don't have to prove the whole curve, but you just have to prove that here. You have to prove that the mixing temperature of scenario B is less than, let's think about this. It's less than the temperature of scenario A at 360 degrees. If this is true, then, okay, scenario B will never catch up. It'll always be below scenario A. But notice that I didn't actually prove this. I proved it only for the combination of constants and parameters for this problem. In fact, I've never seen anyone prove this in general. So if you can do it, well, you might be discovering something new. I'll work on it too. I think it's a question of mathematics. It's a question of some inequalities that you have to figure out. Well, that's been a lot of fun. I think that this has been a really non-trivial video. At least for me, it was hard to get all of this right. So if you liked this whole adventure, then click like and subscribe. This has been an adventure in applied mathematics, which I hope to do more of because it can be really interesting. So I will see you next time.